So today I want to talk about double pendulums, which are probably one of the simplest chaotic dynamical systems. So what makes a system chaotic is that it is highly sensitive to initial conditions in a way that can be rigorously mathematically defined using the system's Lyapunov constant exponent. I'm not sure if I'm pronouncing that right, but that basically comes from an analysis of the system's phase space, which plots kinetic versus potential energy. And you can show that for initial conditions that are within the same neighborhood, the solutions diverge exponentially. And they do this in some sort of limiting process. It uses analysis that I'm not quite familiar with, but it can be rigorously defined, is what I'm trying to say. And double pendulum does meet that mathematical requirement to be classified as chaotic. And I think the best sort of layman's definition of chaos comes from this Edward Lorenz quote, which is one of the main contributors to early chaos theory, where he defines chaos as when the present determines the future, but the approximate present does not approximately determine the future. So in order to derive the equations of motion for a double pendulum, we use generalized coordinates of θ1 and θ2 because for any point in time, we can fully describe the position of the system using just those two coordinates. Their Cartesian equivalents are shown on these bullet points, which we will use in our Lagrangians. So a brief intro into Lagrangians is a system's Lagrangian is its kinetic energy minus its potential energy, and the path that an object will take through space will be the one that minimizes the action, which is defined as the integral of the Lagrangian with respect to time. The solution to solving the problem of stationary action is found using calculus of variations, and specifically the Euler-Lagrange equation, which tells us that the time derivative of the partial derivative of the Lagrangian with respect to the time derivative of your generalized coordinate minus the partial derivative of the Lagrangian with respect to your generalized coordinate equals 0. I know that's a mouthful. So we have the kinetic energy of our system, and then we have the potential energy of our system on the first two bullet points, and then the Lagrangian is just the kinetic minus the potential energy. And at this point, we substitute in our θ1, θ2 coordinates to get our Lagrangian, and then from that Lagrangian, we get our two Euler-Lagrange equations, which are the last two bullet points, and then using some algebra and some trigonometric identities, we end up with these two equations, which express the second derivatives of both θ1 and θ2 with respect to time in terms of other derivatives. And at this point, we can solve the equations of motion numerically, which we do in MATLAB using ODE45, which is a variable step and variable order method. So what ODE45 does is based on the values of the derivatives of the solution, it selects a different time step size, and it also toggles between Runge-Kutta fourth order and Runge-Kutta fifth order for solving the equations of motions. And this helps minimize the error because you can minimize the error due to Runge-Kutta methods themselves by taking the time step to 0. But if you take the time step too far down, you end up with more truncation or rounding error due to the data types that you use to store your variables in your computer. And so there is a sort of optimized way to approach it. And that's where variable step and variable order methods come in. And it also helps to save on computation time. So I machined my own pendulums as a personal project, and I use Logger Pro to analyze the motion. So I had to go through every frame and put a point where both of the masses were, and this was the resulting motion. And I made two of them so that you could try to match the initial conditions to each other, but since it's a chaotic system, you won't be very successful, as we see from here. I have the initial conditions in both cases set to theta 1 equals 90 degrees and theta 2 equals 0. So looking at these MATLAB plots, we see that while the overall shape of both our experimental and theoretical data is more or less the same, after about a second or a half second, depending on how precise you want to be, our solution diverges pretty quickly from our experimental data. And this was when the Edward Lorenz quote really clicked for me, seeing this graph, because these tools that are so versatile in most situations seem to fail pretty miserably for any sort of significant period of time into the future that you want to predict the motion of the system. So ODE45 is a very versatile differential equation solver, and the assumptions for our Lagrangian mechanics model are pretty good. It does assume point masses, but the weights of the rods on my pendulum are negligible compared to the weights or the mass concentrations themselves, and the radius of the mass concentrations aren't very big either, so I don't think that would have made a massive difference. And we do see that for the first half second or so, we get very good results. But this just kind of shows you how chaotic the system is, because this was assuming, a 90 degree theta 1 and a 0 degree theta 2. And while I tried my best to line it up to that, the solution quickly diverges from the experimental data. There are also physical parameters that come into play, such as the damping in the bearings and, again, moments of inertia. And everything just makes it so hard to predict the behavior of the system for any significant portion of time into the future.